Here is the introductory lab, or at least part of it, on filters and oscillators. The first filter we will examine is the ceramic filter, the small orange part in the breadboard. The circuit is very simple. There's an input, an output, and a ground. The ground is the middle pin. The unit is bidirectional, so the input and output are interchangeable. In order to impedance match this device, you need 3 ohm resistors, one on the input, one on the output, and that will allow you to obtain the proper filter characteristics. In this design, there is an input signal from the generator. There is the input signal to the ceramic filter. The only difference in these two input signals is one is before the 3 ohm matching resistor, so it's directly input to the filter, and then the output resistor is in parallel with the output, and we measure that voltage. This is the signals on the oscilloscope. You can see the input signal on the top and the output signal on the bottom. The arbitrary waveform generator, you can set it to the maximum signal level, in this case 10 volts peak to peak. The frequency right now is 455 kilohertz, which is the design frequency of the ceramic filter. The measurement values you will be making are the frequency and the input voltage, the output voltage, and the phase between them. In this screenshot, you can see RMS1, RMS2, and then the phase between the two channels, 1 to 2. The phase measurement is not truly required, but since it is available and we will use it later on in other labs, set up for that value. I prefer RMS measurements in this case because there's a little bit of averaging that goes on in the RMS measurement, makes the values a little more stable. If you want to clean up your signals a little bit, you can use the acquire button and turn on the averaging. When you do that, you'll see a noticeable cleanup of the signal, as now the signal is being sampled 16 times in this case and averaged together. So the noise or the little variations are minimized. If you don't like the screen numbers to change, you can simply push the stop button. That freezes the screen. This also occurs when you download the data to the scope. You don't need to download too many sets of measurements, but download a few just to make your notebook and your data set complete. Remember to unfreeze the display before you change the frequency. We are looking to make the measurements for the 3 dB bandwidth. So as I change the frequency, you can see the output signal changing, right? And we want to measure both the 3 dB bandwidth and the 20 dB bandwidth. The easiest way to do this is to set up a spreadsheet on the computer. On the computer, we see a basic spreadsheet with 4 columns. We have the frequency of measurement from the ARB, the voltage in, the voltage out, channel 1, channel 2, and the phase between them. You can put it in millivolts or volts, just make sure you do your are consistent when you do your calculations. After you do your measurements, you will want to add a few columns. In this case, I have added the volt calculation of Vout over Vn as a linear value, and Vout over Vn in dB. The dB calculation, as we realize, is 20 log of the basic voltage ratio. Now, I am also adding a normalized column Now, a normalized value is a value where we divide all values or all measurements by the largest value. Sometimes in that way it normalizes to 1. This makes it a little easier to plot. One great thing about Excel, of course, is that you can do your plots directly in your spreadsheet, and in fact you can create the plots and enter the data and watch the plot as the data is being collected, which is extremely powerful because that allows you to visually look at the results and also possibly recognize if there's any problems. In this case, I have a plot of the linear voltage over out over input ratio, and below it I have the plot of V out over Vn in dB. So now I have my plot for calculating my dB values and my bandwidths. The bandwidths will have to be calculated at the end of the lab. As we go to the results, we can scroll down. Maybe this point would be typical for the minus 3 dB value. You can see this is 450.6 kilohertz. If I go to the next point that has minus 3 dB, we see a value on the other side of around minus 3.67, and that occurs at 457.38. So the 3 dB bandwidth is between 450 and 457 kilohertz. The peak frequency ended up, or peak value ended up occurring at this point, which is 453 kilohertz. So that the peak value will be considered the resonant value, and then the two 3 dB frequencies, of course, are used to determine the bandwidth. You will also calculate the minus 20 dB bandwidth, and for that case you will find the value where the output is minus 20 dB. In this case it was 500 kilohertz. And on the other side it was 433 kilohertz. So now we have the 3 dB bandwidth of 60 kilohertz.